In the first lecture, we talked about the sources of noise and what causes noise. In this lecture, we're going to look at one particular noise, the most common type, which is thermal or Johnson noise. Thermal noise is due to the random movement of electrons in any particular physical substance. And electrons in a resistor are in a state of constant motion, and it's random motion because there is no connection. If you have a resistor just sitting on the bench, the electrons are moving around the body of that resistor, but clearly they're not coming out of either end because no connections. There are effectively random varying currents flowing throughout the resistor. And over time, these randomly varying components and currents give rise to a small voltage across the resistor. As you heat the resistor up, the electrons get more and more excited, and they get hotter, and it generates a larger voltage. If you cooled that resistor down to zero, there will be no electron movement whatsoever, so there'll be no noise. But we can never reach absolute zero, so there's always some noise associated with electron movement randomly around any substance or conductor. And this is actually what electrons look like under a very powerful electron microscope. And we can also hear them. Because noise is a random voltage, we can use statistics to characterize the behavior of noise. And in any given device or component, there's a huge number of electrons available. There's approximately 10 to the 20 electrons moving around for every cubic millimeter of a component. So in a 1 cubic micron resistor laid down on the top of a piece of silicon, there's anything up to 40,000 resistors moving around in there. And that's a very small resistor indeed. Electrons move very fast, so they're causing about 10 to the 12 collisions every second for every electron. So there's a huge number of statistical events happening in any one piece of time that we want to examine electrons. Because there are so many collisions, because there are so many electrons, we can land up with some very, very accurate statistics to estimate the effect of noise on the components. Because of that, noise looks the same wherever it is measured for a given constant temperature and a constant bandwidth. It's effectively statistically stationary, and we have to use time averages to characterize the behavior of noise over the time period and frequency band that we're interested in. This is kind of what thermal noise looks like. I said that it was statistical in nature, and this is the distribution of the noise voltage appearing across a given resistor versus time. Most of the noise is happening between plus and minus 1 sigma. In fact, we know it's about 68%. But you can get some noise pulses that are peaking up to 3 sigma away. And a good rule of thumb is that the peak value for any component is about 3 times the RMS noise level. And 99.7% of probability is the peak is less than plus or minus 3 times the RMS voltage that you can see that you calculate for the component. This can be important when you're looking at overload performance of circuits. So if you design for the RMS value of overload in the circuit, you may find that you cannot deal with the peaks, which are 3 times larger. Noise voltage can be positive or negative or zero. It's purely statistical in nature. And because of that, we always measure the root mean square, or the RMS value of the voltage of noise. Thermal noise is generated at all useful frequencies that we consider in electronics. And it has the same RMS amplitude at all frequencies less than about 6 terahertz, as long as you measure it within the same bandwidth. And this is what it would look if you plotted the root mean square of noise over a constant bandwidth from 0 up to about 6 terahertz. For any given bandwidth, you always get the same noise voltage, irrespective of frequency. If you increase the bandwidth, and in this example we've doubled the bandwidth to 2 times, you will get an increase of the noise of root 5 times the noise that you had for the initial measurement. So here we have the bandwidth out here. So for bandwidth 1, here we have the RMS value of that signal based here. If we make the bandwidth 4 times smaller, the RMS value goes down by a half because of the statistics. And if we make it even smaller, the RMS value drops yet again. Effectively, we've created here a low pass filter. So looking at it more in this in more detail, here we have the peak voltage divided by the RMS voltage for the blue signal. If we change the bandwidth approximately 4 times, this is it for the red signal, and eventually for the green signal. And at each time we are, the mean frequency can be identical, but the noise is purely dependent on the bandwidth that is surrounding that frequency. So now we know a little bit more about noise. We want to now come on and calculate out how noise is predicted and analysed. And that's what we'll do in our next lecture. Thank you.